Hi everyone, I'm Victor Bar, the Israeli Regional Coordinator of Asteroid Day, and I want to welcome you all to a Space Connects Us event, the OSIRIS-REx Adventures with Dr. Amy Simon. Amy, it's such a pleasure to have you with us today. Today is the 15th of February. Exactly 8 years ago, a meteor exploded over the Russian city of Chelyabinsk, and after realizing the disaster potential of such an impact, Asteroid Day was founded. The main purpose of Asteroid Day is to raise the public awareness of asteroids, both as a threat to Earth's cities and population, and as an exploration of scientific opportunity. The current generation, the Bereshit generation in Israel, is the right generation to encourage to push forward our knowledge and understanding of science, space, and asteroids. After witnessing the arrival of an Israeli spacecraft to the moon and seeing photos of the heavily cratered surface of the moon that are like an open history book for asteroid impacts. Dr. Amy Simon is a scientist of the OSIRIS-REx mission that studies one of the near-Earth asteroids called Bennu, that has a potential to cause a catastrophe far greater than Chelyabinsk, and therefore, she's the right person to promote our curiosity about space, asteroids, and how we can protect our beautiful planet, and set an example for the great contribution of women in all STEM professions. What they will hear from her today will surely help them to choose the right career and education paths towards the future. I want to thank Colleen Fiaschetti, Amin Benzerga, Dr. Stuart Clark, and all of Asteroid Foundation team for their hard work in organizing this event. Also, a special thanks to Dr. Eliat Peretz, a NASA scientist that connected us with Amy. And above all, thank you, Tara, the Jerusalem area leader of the Horizon community of science teachers and space enthusiasts, for helping me in every step of the way. And now to my partner, Tara, I guess you too have some thank yous to say.
Thank you, Victor. We are all very excited for this event. My name is Tara Elad, and I represent the Horizon community for this event. It is a community that was created by the Israeli Space Agency and the Office for Science and Technology in order to spread the starlight as far and as wide as possible. This event is another in a line of events that brings communities together, that helps us spread the opportunity to bring everybody a little closer to the stars, for students, for teachers, and everybody with the love of space in their hearts. I am honored to invite Dr. Amy Simon to tell us about one of humanity's greatest achievements, one of science's most exciting moments. And here we go.
Thank you very much, Tara, Victor. Thank you everyone for joining us today. Let me pull this up for you. So I'm going to be talking about the OSIRIS-REx mission, which is an asteroid sample return mission. So that's an extremely ambitious goal. We're trying to bring back a sample of one of these bodies so we can study it here on Earth. And so I'm going to give you a little background first. What is OSIRIS-REx? Why is it called OSIRIS-REx? Now, for any of you who follow space, you know we like our acronyms, and OSIRIS-REx is no exception to that. It is actually an acronym, and it stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer, which is a lot of words, and you can understand why we use an acronym instead. But the reality is what that is it's telling us the actual goals of our mission. So what did we want to do by going to this asteroid? First is origins. We want to look at a sample of pristine material from one of these bodies left over from the formation of the solar system. So it hasn't been weathered like here on Earth. It hasn't even passed through the Earth's atmosphere to get to us. We're going to bring it back straight from the surface. Spectral interpretation. Right now, most of the asteroids that we look at, we're looking at through telescopes here on Earth. And you're not getting a full picture when you're just seeing that one spot of light in the sky. And so our mission is actually mapping out the surface of the asteroid so we have a full connection from ground-based data to what you see up close to that sample we bring back. Resource identification. We want to know what this object is made of. We know it's a carbonaceous asteroid, but that doesn't tell us about all the minerals on the surface. And that's important in the future, should we ever want to use these asteroids for anything in space. If we use them as a stepping stone to going somewhere else, we need to know if there's anything useful on the surface. Security. We want to measure something called the Yarkovsky effect. Now, this is a tricky little term, but it's actually really simple in principle. If you take any body in space, the sun is hitting it, and the sun will heat up the surface. So as it hits it and those photons hit the surface, it pushes. And so the asteroid gets pushed a little bit by the sun. Well, at the same time, it's a very dark asteroid, so it heats up a lot. And when it spins, as it rotates, that hot side is now pointing to space, and it radiates that heat off. That gives it a push in a different direction. So now you have these tiny, tiny little pushes on the surface that can alter where it's going. And so we want to be able to measure the effect of those little forces to determine how it changes the trajectory of an asteroid. And then Regolith Explorer. So this is documenting the sample site. We want to know down to the tiniest pebbles on the surface what was there before we touched it. And so we were specifically looking for smooth areas of loose soil or regolith. But in addition to that, once we picked our site, we wanted to make sure we had fully documented the area. Those are the goals of the OSIRIS-REx mission. And now you might be wondering, how did we pick Bennu in the first place? So our mission was actually proposed and conceived quite a while ago, 2009-ish, 2010. And so we had a vast number of asteroids to pick from, but we had to pick one that had the right qualities. So first of all, we wanted to pick one that was near Earth. And so in this animation, you see different populations of the solar system. And the green is that main asteroid belt. Out farther, there's actually little blue ones in there. And those are the Trojan asteroids. They're captured in a gravitational well between the sun and Jupiter. But again, these are all farther out. We wanted to get one of these little red ones, the near Earth asteroids, because they're the easiest to get to, but also because we're returning a sample. So we can't be going too far out in the solar system and also return our sample. So this diagram here is showing what the situation looked like in about 2011, but every year we're discovering new asteroids. And so at the time of our proposal, we had to use the set we had and figure out which was the best to go to. And so we came up with this kind of pyramid where in 2010, there were about 500,000 asteroids that we knew of. About 7,000 of those were near Earth asteroids. So those are the potentially Earth-crossing ones, the potentially hazardous asteroids. From those, about 200, just shy of 200, had optimal orbits for us to be able to get a sample and get back to Earth. And then we needed our asteroid to be big enough. If it was just a tiny little rock, we can't easily orbit it, we can't map it out, and we certainly can't grab a sample. And so we wanted it to have a diameter bigger than 200 meters. Once we do that, we were just about 26 asteroids to pick from. Of the 26, we wanted one that was very carbon rich. So one of these very dark asteroids. When you put all those things together, we ended up with Bennu as our target. And at the time of our proposal, it was called 1999 RQ36. It didn't have a name yet, but that was the object that we proposed to go to. And if you look at its designation, it's 101955. It's the 101,955th asteroid that was found. So it took us that many asteroids to find our perfect target. We had actually observed Bennu from Earth before that, using Arecibo, using the IRTF, the infrared telescope, using a bunch of different space-based and Earth-based assets. So we tried to learn as much as we could before we got there. So as we planned our mission, we wanted a suite of different instruments that were going to tell us as much as possible about the surface of this asteroid, both to help us pick our sample site, but then to also fulfill those science objectives of figuring out the composition, of studying one of these bodies up close, and being able to tie it back to all the rest of the asteroids. And so our spacecraft is kind of cube-shaped spacecraft. And we have an instrument deck that has all these different science instruments on it, and I'll show those to you in a minute. We have our sample return canister, and we have our high gain antenna that talks back to Earth. It is a solar-powered spacecraft, so we are running entirely on solar power. And then we have our sampler arm. This is something that was folded up against the spacecraft for most of the mission. And we actually unfolded it. You can tell it kind of looks like a crane or a stork here with a solar array sticking up and a leg sticking down. And this little sample head was the only part that touched the surface whatsoever. So we were not trying to anchor or dig or anything else on the surface. We were just barely touching the surface with the sampler head. This is what our sampler head looks like in action. This is when we were doing testing. And it was kind of a way to vacuum the surface, thinking of like a vacuum cleaner in your house. And what we did is it touches the surface, and once we know it's made contact, we blow nitrogen gas. And nitrogen in particular, because it doesn't react with the surface, we know what it is, it's nice and clean. And just by blowing that gas, it stirs up the surface and forces it through our air filter and picks up all that material. And you can see we stir up a lot. This is actually a test done in vacuum so that we can see how well it works. And that whole canister can hold up to 2.5 kilograms of material. And the pieces we can pick up were up to 2 centimeters in size. So we can pick up dust, but we can pick up rocks up to 2 centimeters as well. So we did a number of tests on the ground with this, both in vacuum under gravity and also on microgravity airplane flights to make sure this was going to work in space. So here's what our instruments look like on the spacecraft. We have a number of cameras. The camera suite was built by the University of Arizona. We also have a thermal emission spectrometer built by Arizona State, a visible and near infrared spectrometer built by NASA, and that's actually the instrument that I worked on. We have a laser altimeter that was contributed by the Canadian Space Agency, and we even flew a science experiment built by students. There was a collaboration with MIT and Harvard to build an X-ray spectrometer to also map out elemental abundances on the surface. And then, of course, once we have a spacecraft flying, we have an antenna. We can do all sorts of science just by having the spacecraft there. And so we have what we call our radio science experiment, and that was mapping out the mass and the gravity field of the asteroid. And we do this with every single one of our spacecraft because we have one there. And just by talking to Earth, we learn about the spacecraft. We learn about the object. So what does it take to get one of these missions to launch? Well, it's not something for people who are impatient. Let's put it that way. This was actually first proposed in 2004. It wasn't picked in that round. It was proposed again in 2006. It wasn't picked in that round. It was proposed once more in 2009, and that's when it was selected. So we began working on this mission in 2009, and then we went through all of our various phases where we designed everything out, we went through reviews, we built it up, we did testing, quite a long ground campaign to get it ready for launch in 2016. And so that's actually our launch that you can see there on the right. And it was actually a really interesting experience to watch one of these launches up close, but realize that your hardware was on the spacecraft. It brings a lot of emotions out because there's worry, there's fear, will it go right? And then just, of course, excitement. So, you know, it was thrilling to stand there and watch it, but then even more exciting once we were getting data back. So we launched in 2016 and we arrived in 2018. Even though this was a near-Earth asteroid, we had to orbit around and go past the Earth again and catch up to the asteroid. And we began our mapping in 2019. Just to bring us up to the present, we're going to be departing the asteroid in May, and we'll be back here on Earth in September of 2023. So what did we know before we got there? Not a lot. We knew it was about a 500-meter diameter object. We knew it kind of looked like a spinning top, almost like two pyramids stuck on each other. We did have some data from ground-based data from Arecibo, and that's the fuzzy picture you can see there. Not a lot of information. From people who are really good at analyzing radar data, we could tell that there was probably a big boulder on the surface, but not much more than that. And so based on what we knew its rotation speed was, about 4 hours, based on its size, we had an estimate of the density. We knew it was very dark. And what we were expecting to see was a fairly smooth surface, probably not as smooth as our model, but we expected to see a lot of dust around the equator. And so this is what we knew before we got there. And then one other point is that its geometric albedo, its reflectance, is about 4%. So that is black, beyond black. It's blacker than the black you see on your screen here. It's very, very dark. So what did we see when we got there? Not that. And this is what we saw on approach. And of course, we were super excited. Lots of features, lots of boulders, lots of rocks, not a lot of smooth areas. And so scientifically, we were super excited by this. But in terms of having to sample this surface, we were also fairly concerned about how we were going to find a good place we could do a sample. Towards the bottom of this rotating image, you'll see a big boulder, and then there's some others higher up. We could see one of those in the radar. We couldn't see the other. And so we were pretty surprised by the rockiness of this object. So what did we discover? Well, even just arriving there, we discovered a bunch of stuff. The first one was that we knew its rotation period. And so we expected to see a light curve as it rotated in phase with what we had observed before. And it was out of phase. And so we already had determined that its rotation rate was changing. And it's partially due to that thermal and solar pushing that I was telling you about. But that also indicates it's a very loose rubble pile. So it is basically a bunch of rocks stuck together very loosely. We also were able to determine that that same effect had moved it very slightly. So it's moved by 185 kilometers in 12 years. So again, we'll be going back and refining those orbit models now that we know about these effects. So at the same time that we found out this was a big pile of rocks, we realized it actually had some surface features that look like ridges. And that means that even though it's this pile of rocks, it's held together pretty well by some internal stiffness. So the self-gravity of these rocks is holding it together. Now, of course, as we have mapped out the surface, we had to come up with nicknames for some of these things because we couldn't keep referring to it as that rock or the other rock. And so we gave them some nicknames, which had to be approved by the International Astronomical Union. And we went with the theme of ancient or mythological birds. So most of the features are actually named after birds, sticking with our Bennu nomenclature. For those that don't know this, Bennu was actually named after an Egyptian bird. It's a crane. It's the companion to Osiris. And so we kept with that theme, the one exception being Ben, and that was actually a mound that rose from the sea. So it's kind of the mountain. And this has been updated since then. There's many more features with official names. But I want you to remember a few of these. We have one called Rock, and we have one called Strix. So I will show you those again. So part of our mapping was to do this distant mapping down to about a 5 centimeter level, but then to get closer and do even better mapping. And no matter what scale we look at, we see rocks. And so this one right here shows the biggest rock on the surface. It's about 60 meters across. If you go down to smaller, this is about 4 meters across the whole image. This is a rock sitting on top of a rock. And you can see it has lots of little fractures in it. So it looks crumbly. From a geological perspective, there's brecciation. That means crumbly rocks, essentially. No matter where we look, we saw every scale of rock you could see. That right there, this big rock, is Strix. So that one that you could see in the map as a tiny little feature in the big map, it's about a 3 meter rock, so 9 feet across. So everywhere we looked, more and more rocks. Well, what else did we see looking at those little rocks? From just a global perspective, we saw the strong signal that indicated an OH band, so water in the past on Bennu. It's not water on the surface now. It's tied into clay minerals. So same as you'd find here on Earth in your yard. It's locked into the structure of the mineral, but it meant that there was water in Bennu's past. Also indications of magnetite, which is an iron oxide. Again, indications that Bennu had water in the past. And our best model of Bennu itself is that it was part of a different asteroid in the main asteroid belt that got disrupted and broke apart, and then eventually kicked out, and it became a near Earth object. And so we think that its parent body probably had substantial water on it somewhere. It's the closest match to what are called the CI and CM chondrite meteorites. Those are just specific types of meteorites. But we don't see that on the surface. We are actually seeing a very uniform surface, except for these little bright rocks that pop up now and again. And those have a very strong signature of pyroxene. And so if you look at their spectrum, they look virtually identical to meteorites that we think came from Vesta. So they either form from that same process, or they could be little pieces of Vesta sitting on the surface. We don't know, but we do see those scattered about in a couple places. Every place else you look on Bennu, from a spectrum point of view, is identical. So we don't see big composition variations on the surface, with the exception of these little pyroxene boulders. So we also looked at the temperatures of Bennu, and this one's really interesting. We expected to see that the large boulders on the surface had high thermal inertia, and that means that they heat up very slowly and they cool down very slowly. On the other hand, we expect the dusty areas, which we thought would be along the equator, to be low thermal inertia, things that heat up really fast and cool down really fast. So think of going out on the sand. It gets very hot very quickly, you burn your feet, but it cools off very quickly at night as well. And what we found was actually the opposite. So those big boulders that we thought would take a real long time to heat up and cool down, they have very low thermal inertia. They cool off and heat up very quickly. On the other hand, the equator has very high thermal inertia. It's not heating up very quickly. So what we think is this actually means that where we expected to see that loose material is actually very compacted. It doesn't have a lot of space between the different grains. On the other hand, the boulders are very porous, very crumbly, as I was showing in that one picture. So that's pretty much the exact opposite of what we expected to find. The other thing is we were looking at Bennu as we orbited around it. So we were seeing it from all different angles. And one of our big surprises is we actually saw a big bunch of particles being thrown off the surface. So this is similar to what you'd expect from, for example, comets, right? Where you see a bunch of ice will suddenly break free and you'll see a bunch of plumes come off. Now this is not gas, this is literally little bits of rock. But you know, at first we thought, well, maybe a little meteorite or something hit the surface and threw them off. And so we mapped out the orbits of these little particles as they came off, and some hit the surface, some go away, some go back into orbit and eventually land. But as we looked, we saw this happen a bunch more times. So Bennu is an active asteroid. We are seeing particles being thrown off periodically. In terms of what's going on, why that's happening, we still have a few theories, but one of them is those crumbly rocks. And so we see surface temperatures that are up to 400 Kelvin or 380 or so, but at night the surface is very cold. And so the rocks are continuously being superheated and cooled, and they fracture. And so if one of them fractures violently, it can throw the particles off. And so this is still an active area of study, but this was really unexpected and interesting. So while all of us were having fun doing our science, we still had work to do. We still had to figure out where we were going to actually sample from the surface. And so the center image here is not actually an image. This is a model of the surface based on our laser altimeter data. So we mapped the surface down to the centimeter level, and we use that to determine what might be a safe place to land or to touch and to grab our sample. And besides looking at what might be scientifically interesting, we came up with 4 prime locations that potentially we could go ahead and sample from. And so those are in the call out boxes. And we named each of them, again, after our birds. But you'll notice that they're all kind of craters. And that's because those are the smoothest areas we could find on the surface. So we needed to be able to safely find a spot that didn't have big boulders in the way, was relatively flat, and then had loose material. From this, we narrowed down to 2, our prime site of Nightingale and our backup of Osprey. And we did closer flyovers to look at them in even more detail. So we got very high resolution views now of the various sample sites while they were trying to figure out what the safest place was to do our sample collection. But that meant we could go back and do more science. And so our latest discoveries, including looking at these boulders close up, and the ones on the left here, you can see have little veins of material in them. We think those might be carbonates. But again, the fact that you have veins inside of rocks is consistent with having liquid in the past, liquid water. And so that was really quite interesting. Besides finding carbonates, we were also looking for organics. And the only real difference between those two things is it carbon with hydrogen or carbon with oxygen? And they both have very similar spectral signatures, so they're a little bit hard to sort out. But it turns out we probably have both, and they're quite abundant around Nightingale, which was our prime sample site. And so on the side here, we have where we saw the deepest carbonate signatures of different kinds and the deepest organic or carbonate as well. And so it turns out our prime sample site was really a very good place to go to try to get those sorts of materials. So as part of our whole plan on how we were going to do this, we had the whole mission mapped out, and we had a very careful approach to go from our nice safe orbit around Bennu to get ready to tag. And we did this in a couple different phases, where we basically would try to match the rotation of the asteroid and practice this before we did it for real. And so this animation shows the exact sequence we did. We got to checkpoint, which was a point over where we wanted to sample, and you'll see a little graphic that shows our sample site down at the bottom. We descend to match point, where we match the rotation of the asteroid. And then finally we touch and go. So tag is touch and go, and you can see it touches and goes pretty fast. And the idea here was to very carefully make sure we line up with our sample site. We're moving at the same speed as the asteroid, so we don't just get kicked off by hitting at the wrong angle or at the wrong speed. Very slowly, literally 10 centimeters per second, move to the surface, barely touched. And then once we've made contact, blow our nitrogen and then back off. Now, we did have one contingency that we could do here, which was that once we made our contact, if it felt like we were pushing off the surface, they had a mechanism to push it down harder. But that was only if it didn't think it had made good contact. And we had the ability to do this 3 times if we had to. So what did it actually look like? This is our camera that was looking at the tag arm during the actual event. And this is sped up again. It was 10 centimeters per second. It was moving really slowly. But you can see, boy, did we hit that and touch it. We made good contact. And so even though it's going a little fast, what you're seeing is we turn, we touch, blow the nitrogen and back off. And you can tell just by the fact that everything goes very dark, we stirred up a lot of stuff. There was dust flying in every direction. So what was the actual timeline here? We were moving down at 10 centimeters per second. We made contact. If you look at that in really slow motion, you'll see that we actually break apart the rocks we touched and sink. So we keep sinking into the surface. So after contact, 1 second after contact, we blew the nitrogen for about 5 seconds. That's when you see all the particles go flying. We're still moving at that point, down 4 centimeters per second. We sink into the surface, 20 to 50 centimeters actually, before the thrusters fire and push us backwards at 40 centimeters per second. So we're not moving fast, but there's a lot going on in that timeline right there. So we do think we actually pushed into the surface pretty substantially. So after we back off, we had to tell if we had a sample whether or not we had to go back and do this again. And so we had 3 different ways to check. The first was to look through the side of the sample head itself. We could see sunlight through the side of it and see if there was material in there. We had little contact pads around the edge that had metal wires, almost like Velcro or steel wool, that could hold on to little bits of dust. So we could look and see if we had anything in there. And then our last thing to do was to actually keep that arm extended and spin the whole spacecraft and see if its mass had changed from before we had done the sample. And so that was our final determination to tell how much material we got. So we started to do this. This is what we saw when we looked. There's stuff coming off. There's stuff everywhere. If you look real close at the contact pads, there's material stuck to all of those. But with the sunlight on the side here, you can see this washed out bright part here. You see a dark shadow. You see a wavy rim here. Our whole sample head was full of material. And this wavy rim is because some of the big rocks were probably propping open our flap a little bit that seals the sample in. And so we had so much material, it was falling back out again. So at that point we said, okay, we are not spinning this. We are not going to throw all of our nice sample out into space, and said, stop, we're gonna go ahead and put this in the canister and go from there. So then that was our next question, is everything is covered in dust. We're clearly throwing dust off and pieces off in every direction. Will we be able to seal our sample capsule? And so this is what it looked like. We had cameras that could watch as we did this, and you can see as we put the head over the sample capsule, and then as it clicked down into place. So that was first confirmation. We got it in, there was no problems. The only part left now was sealing it. And so this is our video that shows us sealing the sample head in. There's not dirt and crud all over the place, so it closed cleanly, which was the primary. So everything is now set for us to return to Earth and send our capsule back. So what's going on now? So because we didn't want to fire the engines, we didn't want to do anything until we got that sample sealed in there nicely. OSIRIS just continued to slowly drift away from the asteroid, 40 centimeters per second, while we planned everything out and made sure we understood our departure timeline. It turns out that we've got plenty of time to go back for one last visit, and we're going to do that in April. And we will do this to check out the instruments, but also to look at our sample set again and see what's happened to the surface. How much did we disturb by doing the sampling? And does that change what it looks like? And so we'll be doing this at the same attitude as one of our observations that we took in 2019. So we'll have a before and after that we can compare this to. And then we finally depart in May. Our departure burn is coming up. And then we have to do that same thing we did going out there, where we now have to catch up to the Earth. So we'll go around, and it takes us until 2023 to get back to the Earth. As we approach the Earth, we jettison that capsule. The spacecraft diverts and continues on. It could go to another target if that's decided. But in the meantime, that sample canister would then come back down through the Earth's atmosphere, parachutes, and it lands in the Utah desert at the test range, same place where other samples have returned. So that's where we are on the timeline. And I can say, stay tuned, but we're excited to see what we get back here on Earth. And I will stop there and leave this up. This is all the links where people can follow along with our mission on Facebook, on Twitter, or on our main website, asteroidmission.org.
Amy, that was incredible to listen to and to watch. And I can tell you guys, this is going on a multi-level platform event. We're here on Zoom, we're on live broadcast on various places, and there are people communicating with us. And you just blew everybody's mind. The images are amazing. A lot of people didn't know you are going back in April. I am extremely excited, and I'm calming myself down because we have been gathering questions as a lead up to this event from all around the country. We had students write in, we had professionals and teachers write in. Victor and I snuck a few questions in because we're privileged, and we can't wait to ask you some of the questions. Many of them, I have to tell everybody, many of them were repeated questions. So these are coming from a lot of people around who are very, very interested in this. And I feel like the more people who would listen to what you just told will just be fired up with enthusiasm for asteroids everywhere. So we're going to hit it off. I'm going to start asking questions. I'm telling everybody who's listening to us, we're going to try to get as many questions in as possible. I will apologize. We have so many questions, guys. We scratched off those that Amy already addressed. We're going to start with the ones who got the most, to ask the most times, and we're going to run down that until the time is done, and let's begin. Okay, first question, Amy. What, in your opinion, was the biggest challenge the mission faced? You've just described this whole timeline. Many things were occurring at different points, a lot of technical challenges, a lot of firsts. What do you feel was the biggest?
Yeah, I think our biggest challenge, of course, was finding a sampling site that we could safely get to, and figuring out how to navigate that very rocky terrain. And part of what we ended up having to do was literally make that model and have computer programs that could analyze the images that we're feeding back and say, okay, that's where that rock is, adjust. And so it was very complicated terrain mapping to be able to get so close to our sample plane and pretty much nail it right in the center where we wanted to be.
Incredible, incredible. Okay, next question. How did the minutes before receiving the information that the maneuver was a success feel?
Yeah, there was a lot of anxiety, a lot of excitement. Of course, we were nervous, but we were just thrilled, waiting, and everything went so smoothly. It was just the dedication of the engineers on this program was incredible. And so we were so excited to see those first images, and when we saw it, we were blown away. I mean, just like the surface, we were blown away.
Do you have an estimate of how much mass is actually in the capsule? How much is planned to be en route back to Earth?
Mm-hmm. So we had a requirement to bring back at least 150 grams, which doesn't sound like that much, but that's because that was the accuracy with which we could measure when we spun the spacecraft. The sample collection canister can hold up to 2.5 kilograms. So it would just depend on the density of the material. But we know we got way more than the 150 grams. That's just the fact that the canister was so full. So there's different estimates out there between 500 grams, 1,000 grams. We won't know until we get back exactly because we didn't do that mass measurement, but it'll be sizable.
Is there a chance that reentry might damage the samples?
Right. Reentry is the next scary point, right? We have to release from the spacecraft. We have to enter through the atmosphere. It has a pretty solid heat shield on the front of it. The canister will get hot. And so if we were trying to do ice, something like that, we would probably evaporate it. But because these are rocks, that's not so much concern. We do have our parachutes. This sort of system has been used before. It was used on previous sample missions. And so we're confident in it, even if it hit the ground, that everything would survive and be fine.
On past sample return missions, specifically moon rocks, the samples were usually divided, and sometimes a small fraction of a sample is kept for future generations, usually under the assumption that future generations might develop more sensitive machinery, might be able to get data that we right now in this present are not able to. Can you tell us a little bit about the plan for the actual return? If it's 0.5 kilogram, that sounds like a lot of people are going to get some asteroid rocks.
Right. So the original plan was this 150 grams, which really only guaranteed 60 with the uncertainties on the spacecraft. And even with that, if we had only gotten that small amount, the plan has always been to archive at least 75% of it. Exactly for the reasons that you say, because in the future, people will have new techniques, they'll have new instrumentation, they'll have new questions. And so no matter what, a sizable fraction of that will be archived. And then small amounts are set to go to each of the member countries that contributed to the mission.
Amazing. Can you give us an example of what we can learn about Bennu in laboratories on Earth that we cannot do with the current scientific payload that is on OSIRIS-REx?
Yeah, that's a great question. So there's limits to what we can fly, right? There's only so much mass, so much power on aboard a spacecraft. And so all of our instruments are running less power than your toaster, than a light bulb. And these are fairly sophisticated scientific instruments, but there's still only so much we can do with that little power and that little mass allowed to us. And so our spectrometers probably do the lion's share of trying to figure out composition, but we're still trying to figure that out from a kilometer away. So you're standing way down the road and looking and trying to figure out what everything's made of. And so our laboratory samples, you can grind it apart, you can look at it through a microscope, you can react it with other chemicals, you can figure out down to the molecular level what you have in your sample. And we just can't do that from a remote spacecraft.
Would you yourself be involved in the analysis of the samples upon return? Are you part of that as well?
No, I'm not a sample scientist, so they're not going to let me in the lab, and they're not going to let me touch things. But I've been more involved in building the instruments that are looking remotely.
Was there, you spoke, you mentioned international cooperation, you mentioned a few that were also part of building the instruments, will be also returning, receiving some of the return sample. Specifically, was there a cooperation between the OSIRIS-REx team and the Hayabusa team, who are operating on many similar objects?
Yeah, absolutely. So, we had a little friendly competition over who was going to get more samples. But in all seriousness, on a scientific level, of course, we always collaborate, but it was important to us to also use their lessons learned, because the first Hayabusa learned lessons about sample collection, but the second Hayabusa, when they first were around their asteroid Ryugu, and they shot an impactor at the surface, and we watched their rocks crumble, for example, that made us feel a whole lot better that the same thing would happen on ours. We weren't going to hit a hard surface. And so we were able to have those collaborations, those conversations, and also now we'll be able to compare those two asteroids and their samples. And so absolutely, there's been a very strong collaboration.
Amazing, amazing. The asteroid race. Okay, our next few questions are a little bit different. Up to this point, most of those questions were very scientific, came to us by professionals, a lot of adults who wrote in. We're going to touch base with a little bit of questions who came from our younger audience, our younger students. They're a little bit more conceptual and a little bit less scientific. And we want to start with the one which can we hear your story about how did you come to work for NASA? There are many little girls out there who are passionate both about rocks and space. And we would love to hear a little bit of your story, a little bit of the road that led you here.
Sure. So growing up, I loved science. I loved rocks, even though I don't get to study them myself. I always knew I wanted to do something in science. And I think my inspiration when I was a kid was the space shuttle program. And NASA, Sally Ride, I really wanted to do that. And that led me to study as much science and math as I could in high school, but also in college. I went to the Florida Institute of Technology, which is right near Kennedy Space Center. So I got to see plenty of launches, which of course just spurred my passion to do this even more. And I went on, got my PhD, and eventually there was the chance to work at NASA, working on the Cassini mission at Saturn. And, I applied and got accepted. So I've been at NASA for about 20 years now. And I've seen it change quite a bit over that time. There were not as many women when I first started there, and there's quite a few now. So yeah, it's been a great career, and it's been, a dream. I'm not sitting on a space shuttle, but I get to drive spacecraft out in space and see things people don't get to see. So yeah, it's been fabulous.
That was a great segue for our next question, because many of our students also wanted to know if being a female lead scientist in the NASA team, how does it feel? And one of my students actually asked, do you get to boss people around, was the actual question. So do you get to boss people around, Amy?
Well, I get to lead projects. I try not to be a bossy person, but no, it's as I say, it's definitely changed. When I first got at NASA, in my group, there weren't any other women, and now it's, I think, almost 50-50 even, maybe not quite, but I work with a lot of very, very smart women engineers and women scientists and, women managers who do get to boss people around. But in science, we're much more collaborative, so we work as a team, and really any success I have is always due to a bunch of other people as well. And so we try to remember that you work better as a team than you do if you're too bossy.
Amazing. Okay, what are your plans for future missions? I know that you're still on, the team still has a lot of work, especially if we're going to have another visit, especially expecting re-entry, and especially if you were going to use the same vehicle for another go around. But looking ahead, are there dreams beyond OSIRIS-REx, beyond Bennu calling your name?
So we're always looking forward to our next missions and what else we're going to be working on. The one that's in the queue right now is the Lucy mission, and that is a mission to Jupiter's Trojan asteroids, those ones way out there past the asteroid belt. And that mission actually launches later this year. So we're also building and testing right now for that, and getting ready to do that mission. And that one will be flying by. We fly by quite a number of them, actually. So it's going to be really interesting to see how much different they are than Bennu.
Okay, now we have time for a few fun questions, which we left for the end in case that we're going to run out of time, and we have a few more minutes. So they're a little bit more casual. Okay, first of all, people want to know, how much is the asteroid worth, and can you sell it?
Okay, I don't know what it's worth. It's, the majority of the material on the surface is carbonates. So not sure you do much with that. Yeah, I don't think that it's something we're going to go mining.
So not that one, not Bennu. We're not hauling that one back to Earth. All right. Okay, next question. Is Bennu dangerous to Earth? And have you learned how to stop it if it threatens Earth? I know especially the Planetary Society is very worried about near-Earth objects in general, asteroids. Everybody say it's a matter of time. It is just a matter of time before there is something coming by close enough. I know it was a partial agenda for figuring some of the options out in case in the future such an occurrence would happen. What can you tell us about this?
Sure. One of our objectives was security, figuring out how these asteroids' trajectories get altered and so on. So Bennu is a potentially hazardous asteroid. Just being a near-Earth object, it is. It currently is number 8 on the list of ones that could impact the Earth, and its highest probability is about 1 in 2,700 in about 150 years from now. So no time soon. There's other ones that are tiny that have higher probabilities. But Bennu, as we said, is fairly sizable. It's pretty big, 500 meters across. So it's not something you really want to be coming towards the Earth. On the plus side, we do know it's a rubble pile. We do know that parts of it break apart pretty easily. I think we're going to be analyzing a lot of that in a lot more detail. There's certainly other missions out there that I'm not part of for asteroid redirection and looking at what one could do if we thought something was going to hit. So I think they're going to take some of the knowledge we've learned from Ryugu, that we've learned from Bennu, and use that in their studies. But it has a low probability in about 150 years of impact.
Amazing. Okay, we have a live question coming in from Facebook, which is very interesting. So we're going to pop it up, even though we're in a casual place. We're going to put our scientist hat back on. Prior to re-entry, using the same method that many satellites use by putting a bit of your sample in a small case in orbit to be captured for analysis. We've spoken a bit about the dangers of re-entry, falling, heating, landing in the Utah desert. Is that an option that you guys even considered? Is it an option maybe for future missions?
Yeah, we certainly can't do anything like that now because that's not part of our mission plan. We don't have anything set to do that. Because this was a technology used for previous missions, this was our going in plan. And of course, all the risks were assessed and determined that they were acceptable and that this was what we would do. But that's certainly a possibility. I think some future sample return missions have discussed that sort of thing, putting things out to the space station, for example. But that's not part of our plan.
All right, and now I believe, unless there's going to be a few more live questions coming in, I feel like this is our last question of the night today. You partially spoke about why OSIRIS-REx didn't return immediately, about the timeline that is still ahead of us, and there's a question about risk taking, because right now we're in a position where the capsule is for sure closed. We have the sample in. It is very tempting to go back and bring the sample. We have a sample. Why are we taking a chance? Another visit and spending more time figuring things out might actually put in danger what we already accomplished. Is that not true? I kind of tell us a little bit about the calculations behind that decision.
Okay, sure. So first of all, on the when we come back part, there actually were limits on when we could come back and be on the right path to come around and catch up to the Earth. And so that constrained our return date no matter what. We couldn't just leave early if we wanted to. The original timeline also included time for us in case we had to attempt to sample again if we didn't think we had gotten a sample. So obviously that part's not true. In terms of going back and taking one more look, that's very, very low risk because it's a microgravity environment. We're not talking about going back to Mars or something like that. And so we're still in the vicinity of Bennu. It's not a big deal to take that look and see what's changed on the surface while we waited for that window to open where we could safely come back.
Perfect, Amy. It has been beyond honor and beyond pleasure and a great opportunity to hear more about this and more from you. You have been incredibly professional and enlightening. Thank you so much, truly. I think we will be wrapping up. I will say a few things. I would like to thank Space Connect Us, which has truly connected us, has been incredibly professional, has babied Victor, myself, and Dr. Simon throughout this procedure, and tried to make sure that we get to as many people and we make this as professional as it came out, as it turned out. And thank you so much, especially Colleen, and all of the partners that Victor brought along from Asteroid Day, all of the asteroid enthusiasts who are the real army behind mapping the night sky and being ready for whatever comes our way next. For Dr. Peretz, who made all of these connections originally happen and then just let us go and allowed us to have all this fun together. For everybody who's watching and all of the Horizon members who came on to share this knowledge, I invite you to use this footage, use Amy's presentation and our questions, and tell everybody out there, tell all the students about what we are accomplishing every day out there in space by amazing people like Dr. Simon, who are also very generous with their time. Victor, anybody else? Did I forget anybody? I probably forgot a ton of people. Help me out.
Yeah, so I want to say a few words myself. So thank you very much, Dr. Amy Simon, for this brilliant talk. It was truly mind-blowing. We learned so much today, and I hope this talk and future ones will inspire the public to learn even more about space and asteroids. Thank you all for attending this special Asteroid Day Israel event, Space Connects Us, with Dr. Amy Simon. The event will be available on Asteroid Day website, Asteroid Day Israel Facebook, and the Horizon YouTube channel. So good night, everyone. Thank you.